Hello everyone, welcome to the final part of complex numbers, roots of unity. Roots of unity is basically solving the equation z to the power of n equals to 1. So over here you find a formula to find each root. You have each root equals to cosine 2k pi over n plus I sine 2k pi over n. But we'll discover how we get to that later on. So let's first do a question. Find the roots of z to the power of 6 equals to 1. Okay, so let's solve this. Z to the power of 6 equals to 1. So this means that if we square root both sides, we get z cubed equals to plus minus 1, which means that z equals to plus minus 1. Right? Wrong. Actually, there are 6 solutions to this equation. This only gives 2. This is our normal way of finding solutions. But now that we've learned about complex numbers, we actually know that there are 6 total solutions. Why is this so? If you remember from our conjugate root theorem, we can always express any polynomial in terms of, let's call all the roots z1, z2, and we can have this all the way until z6. So actually, we have 6 different roots that we need to find. So let's see how to find all these additional roots. Okay, let's express 1 in terms of polar form first. So we have e to the power of I, 0. While this 0 is technically correct, it doesn't net you every single possibility. So if we have 1 on this argument diagram, if we have an argument of 0, that's right, but we also can have an argument of 2 pi. We can have an argument of 4 pi. We can have an argument of negative 2 pi, and all this still gets us 1. So in order not to miss out on all the solutions, what we need to do is take 0 plus 2k pi, where k is an integer. I'm sure you probably remember the 2k pi from an earlier video when we were doing the polar form. So what we can do is first find what z is, which is just e to the power of I, 2k pi over 6. And you realize this is actually the same as this, right? When n equals to 6. Sorry, I forgot to write that k is an integer. So carrying on, let's find out all the roots by substituting values of k. So z can be equals to e to the power of I 0 when k equals to 0. When k equals to 1, we get pi over 3, so our argument. If we get k equals to 2, we get 2 pi over 3. If we get k equals to 3, we get 3 pi over 3, which is just pi. And if we get k equals to 4, we get 4 pi over 3. But again, since we are presenting this as a final answer, we probably do not want to use 4 pi over 3. We want to look at the principal argument. So what I may want to do is take k equals to negative 1, and I get negative pi over 3. If I take k equals to negative 2, I get negative 2 pi over 3. Now, what about e to the power of I 4 pi over 3? Actually, that's just the same as this, if you minus 2 pi to the argument inside here. So as you can see, this tells us 2 facts. Firstly, as long as we have 6 different distinct roots, if we substitute k more than 6 times, this means that we'll get repeated roots. As you can see, k equals to 4 will be the same root as k equals to negative 2. And next, this also means that I probably want to substitute k equals to 0 and all the positive values of k until it reaches beyond the range of the principal argument. Then I'll substitute negative values of k until I reach the end. And that nets us all the possible roots of z to the power of 6 equals to 1. Okay? So what we can do is express all these roots in a circle. What does this mean? Remember that each of these have a magnitude of 1. So our first root over here is 1. Our second root, which we call w, is just e to the power of I pi over 3. Our third root over here is just e to the power of I 2 pi over 3. And if you see carefully, this is just w but squared. And that's why I write this as w squared. This is w cubed, this is just e to the power of I pi, which is w but cubed. And again for w to the power of 4, w to the power of 5, just note that e to the power of I 4 pi over 3 is the same as e to the power of I negative 2 pi over 3. So this shows that we can represent all our roots by 1, w, w squared, w cubed, w4, and w to the power of 5. All of these will be given as points in a circle with magnitude 1, as well as, if you see here, each of these angles are pi over 3 because you're just adding pi over 3 to each angle over here. This is how you usually want to draw the roots of unity, in the form of a circle. So let's look at the next question. Given that w is a root of z and w equals to e to the power of I pi over 3, which we have written over here, w is a root of z. In fact, it is e to the power of I pi over 3. Now we want to show that this whole thing equals to 0. So let's take a look at this. This is actually the sum of all distinct roots. As you can tell, 1, w, w squared, you're just summing all these up. And to provide a little bit of visual perspective on this, if you look at this orange point in the middle, if you pull on the string in all these different directions, right, it actually doesn't move because all the strings tend to cancel out. So that's just a visual, very like non-mathematical way of showing that the sum of all distinct roots will be equal to 0. But how do we actually prove this? We know that z to the power of 6 equals to 1, so z to the power of 6 minus 1 equals to 0. And since w is a root of z, this also means that w to the power of 6 minus 1 equals to 0. And I want you to remember one result, okay? If you have any w to the power of n minus 1, this can be also written as w minus 1 and then 1 plus w plus all the way until w to the power of n minus 1. If you want to see why this works, you can either do synthetic or long division for this over this, and you should get this. So what I can say is that w minus 1 and then 1 plus w squared all the way until w to the power of n minus 1, in this case is w to the power of 5, is equals to 0. And since we know that w equals to this means that w minus 1 is definitely not equal to 0. So since w minus 1 is not equal to 0, this means that this other side, which is 1 plus w squared plus w cubed plus w4 plus w5 must be equal to 0. Now let's move on. Find the area of the quadrilateral marked by 1 w squared and w cubed. So again, let's look at this Argand diagram here. I've nicely labeled out 1 w squared and w cubed and drawn the quadrilateral in green. So if we look at this, we're actually utilizing that all of these angles are just pi over 3. And how does all the angles being pi over 3 help us? If we want to find this yellow area, your green area is just 3 times of this yellow triangle. Each of these yellow triangles are the same. Why? Because they all have an angle of pi over 3. And because these 3 yellow triangles are the same, to find the green area or the area of the quadrilateral, what this is going to be is 3 times this yellow triangle. We'll take 3 times half AB sine C. In this case, your A is this, your B is this, and your sine C is your sining pi over 3. So you have half AB. In this case, you know that the magnitude of this and this are both 1. And then sine C, which is sine pi over 3. Sine pi over 3, you know that this is just root 3 over 2. So you have 3 times half times root 3 over 2. Which if you simplify this would just be 3/4 root 3 units squared. Okay, that's all for roots of unity and the properties of the roots, as in how to use the circle in order to find area and to show that the sum of all distinct roots equals to 0. Okay, let's move on to roots of a complex number. So earlier, we had roots of unity. Now we have z to the power of n not just equals to 1, but equals to a complex number in the form of x plus yi or r e to the power I theta. So again, let's just ignore this bit. Let's do the question. Solve the equation z to the power of 4 equals to 1 minus I. Again, earlier, remember we converted 1 to e to the power of I 0 or e to the power of I 2k pi, right? So we're going to do the same thing. We're going to convert this into polar form. So we know that the magnitude of 1 minus I is just square root 1 plus 1 or square root 2. Then we have e to the power of I negative pi over 4, because this is in the 4th quadrant. The 4th quadrant over here, so this will be negative tangent inverse 1 over 1, which is just negative pi over 4. Alright, and earlier we did 0 plus 2k pi, so again we're going to add 2k pi so that we don't miss out on all the extra solutions. Again, this is only for integer values of k. So let's simplify z. Z equals to the 8th root. Don't forget to simplify the magnitude. This is just my common mistake. I always forget to simplify the magnitude. And then I'll divide everything by 4 over here. So this becomes negative pi over 16, and then 2k pi over 4. Again, this over here is essentially the same as this. So I'm applying the formula, but using a bit of conceptual understanding instead of just blindly applying this formula. So if you remember, what we do next is just substitute in values of k. So the first value of k I like to substitute is always k equals to 0. So in this case, k equals to 0 will just be negative pi over 16. Let's say we take k equals to 1, we'll get e to the power of I 7 pi over 16. If we take k equals to 2, we'll get e to the power of I 15 pi over 16. So now that we get 15 pi over 16, this is actually very close to pi, right? Which is very close to the upper limit of the principal argument. So what we want to do is actually take negative values of k. E to the power I, and then let's take k equals to negative 1. We get negative 9 pi over 16. Again, I'm substituting k equals to 0, 1, 2, and then negative 1 over here. Okay, so we have solved this equation with our 4 unique roots. Now, what we need to do is prove that this entire thing equals to 0. So, similarly, the sum of all distinct roots for roots of a complex number is also equals to 0. But don't worry, they won't ask you to prove that. We can just use the result. So, the fact is that the sum of all of these equals to 0. So this is going to be very long to write, but I'm actually going to write this in terms of trigonometric form. I'm going to write cosine negative pi over 16 plus I sine negative pi over 16. Okay, I've written out this really long statement where it basically adds these all together and converts this into trigonometric form. You see over here, e to the power I negative pi over 16 becomes cosine plus I sine, and here becomes equal to this, same for this, and same for this. And this actually just equals to 0. What you want to prove again is that all the cosines equals to 0. So if you want to isolate all the cosines, we can just say that the real part is equals to 0. Okay, so if you look over here, I've just taken all these and said that the sum of all that will be equals to 0. This is because I'm just taking the real part. Alright, you can see that we're almost there. We're just missing out one thing. This cosine pi over 16 is negative. And this cosine 9 pi over 16 is also negative. So what can we do? We need to utilize the fact that cosine of negative x is equals to cosine of x. This is because of one reason, which we will learn later on. Cosine is an even function. If you're not convinced, you can look at transformations and trigonometry to help you understand why this is so. But for now, we can just accept this. So this is just cosine pi over 16, and then this will stay the same as cosine 7 pi over 16. Let's just put the 9 pi over 16 there, and then flip the sign, and then plus cosine 15 pi over 16, which will be equals to 0. This is a summary sheet for roots of a complex number, and this is all the questions from Roots of Unity. Finally, this is the complete summary sheet for complex numbers. Thank you so much for watching. I hope you've gained a much greater understanding of complex numbers now that you've watched all the videos.